So now we're going to be covering the RANSAC algorithm. So the algorithm is a very simple one, which has majorly three steps. So firstly, you have select random sample of minimum required size to fit the model. Then compute a putative model from the sample set. Then third, compute the set of inliers to this model from whole data set. Then repeat 1 to 3 until model with the most inliers over all samples is found. So now key points: sample set, a set of 2D points as shown in the image, where some points are outliers displayed in red. Algorithm: select a random sample of the minimum required size to fit the model, compute a putative model from the sample set, and compute the set of inliers that fit the model from the entire data set. Now repeat the above steps until the model with the most inliers is found. Random sampling: the algorithm randomly selects subsets of points from the data. In this example, some points are clearly outliers shown as red dots, which should not contribute to the model. Model computation: from the selected sample points, the algorithm computes a putative model, for example, a line, a plane, or other geometric models. And inlier identification: after hypothesizing the model, the algorithm calculates which points in the entire data set fit the model well, labeling these as inliers. These inliers are points that are consistent with the model. Now repetition: the process of selecting samples, hypothesizing the model, and identifying inliers is repeated many times until the algorithm finds the model that best fits the largest number of inliers. The key strength of RANSAC is its robustness against outliers, since it iteratively refines the model to ensure that outliers don't skew the result. Now, RANSAC for line fitting example. So randomly select a minimal subset of points, hypothesize the model, in this case a line, compute an error function. The error function measures how well the model fits the points in the dataset. Then fourth, select points consistent with the model. The points that fit the model well are identified as inliers. Repeat. This process continues iteratively, adjusting the model until it fits the most inliers. So that's it about line fitting for RANSAC. Now RANSAC conclusions. So the good ones are it is robust to outliers and the number of hypotheses n is taken sufficiently large, hundreds to thousands, that RANSAC gives very similar results every time. And bad, its cons are it is not good for multiple inline structures, getting those, and computational time goes quickly with fraction of outliers and number of parameters. So let me discuss this in depth. So the good points or the pros are basically it is robust to outliers. One of RANSAC's primary advantages is its ability to effectively deal with outliers. It can fit models even in the presence of substantial noise and incorrect data points. Large number of hypotheses. When a large number of hypotheses n in hundreds of thousands are used, RANSAC tends to give consistent and reliable results, effectively reducing the impact of outliers. But its disadvantages or cons are computational time growth. The computational complexity of RANSAC increases rapidly as the fraction of outliers in the dataset grows. This happens because more iterations are required to ensure that inliers are correctly identified. Similarly, the number of model parameters, such as 3 parameters for a line or 8 for a homography matrix, increases the number of computations required. And also not good for multiple inlier structures. It is not effective when there are multiple inlier structures present. If the data contains multiple models that fit different parts of the data, for example, multiple lines or planes, RANSAC will likely only find the most dominant structure and the other structures will be ignored, as it assumes a single model fits most of the data. So again, repeating these points, strengths. The key advantage is its robustness. It can work with data that contains a significant number of outliers without being skewed by them, provided it has enough valid data inliers. Large number of hypotheses allows RANSAC to repeat the process of fitting the model, ensuring that it finds the most suitable one. And weaknesses, the downsides include the increased computational time as the number of outliers grow. The more outliers there are, the more iterations RANSAC will need to correctly identify inliers. Additionally, as the complexity of the model increases, fitting a homography instead of a line, more points are needed and the algorithm has to process more combinations, making it computationally expensive. Furthermore, the algorithm struggles in scenarios where there are multiple valid models or structures in data, as it is designed to converge on a single best model.